closer lead or not, it doesn't matter. And as we were increasing the voltage or amplitude of the vibration, you can see a lot of cold mist is coming out of that base fabric. The interesting thing in this technology is that this cold mist is not warm at all. It is just as cold as room temperature, and that's why we could reach to such a high drawing efficiency. So this process goes on and on for somewhere about 4 or 5 minutes, and we could reach to the complete dry in 4 or 5 minutes. So with the prototype that you saw, and ability to draw a small size clothing in a few minutes at much higher efficiency. As a matter of fact, we put a small pan actually that is the pan from my 2-year-old son, and we could actually draw small pieces of fabric, so small pieces of clothing. So this is the largest prototype we have so far, but we are working on scaling it up. So let's look at the results, some efficiency results of this prototype. So the x-axis here is the remaining moisture content of different configurations. Always we start with 57% initial moisture content, mainly because when the clothing comes out of the washing machine, usually it has 57% moisture content, and we drive down to, most of the cases, down to 20% remaining moisture content. What we realize is that below 20%, the efficiency of the drawing is, through this method, is not very good. So all this technology is working the best for moisture content above 20% and even above 57%. So it can draw anything from high moisture content down to 20% very efficiently. So the y-axis here is joules per gram of water removal that we put on the piezoelectric transducers. And we put 2 lines. One line is the energy needed to evaporate water, 2400 kilojoules per kilogram of water removal. And also another green line here is typical recipe fitting based conventional dryer efficiency range. So anything below these 2 numbers are better than evaporating dryer and shows a better performance than the conventional system. And as you can see, in most of the cases and most of the cases that you configuration that you run, the efficiency is or the energy consumption is significantly lower than evaporating drying. Means that the efficiency of the drawing is much better than the conventional evaporate-based drawing. This slide shows the drawing time versus remaining moisture content for the same test. For most of the cases, actually the drawing time versus remaining moisture content was following almost a straight line. In some cases it was faster, in some cases it was slower. And this table actually summarizes the results we got. So the best results we got so far shows that the efficiency of the drawing could be as high as 16 or even 18 pounds per kilowatt hour of energy input to the system. And putting in perspective, the conventional dryers have an energy factor of about 3.5. And this is a significant improvement over the conventional dryers. Definitely, we don't have the full system, so there are a lot of other components that need to be added to the scale of system. But definitely, it shows a promising results so far, and showing that we can actually dry much more efficient than evaporating water. So, at this point, we are actually at the end of the year 2 of the project. When we started the project, actually the first prototype we had, we could dry 1 square inch of the fabric. But at this point, we can dry somewhere about 200 or 400 square inch of fabric with our prototype. And from efficiency point of view, we started with energy factor of somewhere about 3 or 4. And at this point of time, our energy factors are beyond 12 or 15, as you saw in the previous table. So we significantly improved both the efficiency and the scale of the system so far in the last 2 years. And the next step would be we further scale up the system, and probably we are going to retrofit the full-scale dryer drum with the piezoelectric transducers, and also design some alternative systems for the full-scale dryer other than the conventional full-scale drum dryer. And also, we have to show that we are going to achieve the energy factor more than 10 and drying time of less than 20 minutes in the scale of the system, and that's so far. So some frequently asked questions. We have demonstrated this technology to many groups, and they come back with so many questions, and I summarized a few of those questions here, and I'm trying to answer them as short as briefly as possible. One of the questions is that what happens with the mist after it's produced? So as I described in this presentation, it will be either vented out of the building or can be collected with the mist collection mechanism that we designed under this project. Another question is, who is the owner of the IP on this technology? The answer is that ORNL is the owner of the IP, and actually the IP only belongs to Oak Ridge National Lab and not other entities. Does the technology dry material other than the fabric? The answer is that it depends. We would like you to contact us if you have any specific applications, and we can help you to figure out whether this technology can be applied to your system or not. But in summary, what we have done so far, our main focus was on fabric drawing, and we showed the technology showed a great potential in that area. We also put a little bit of time and showed that the technology can be applied on for paper drawing and also cellulose drawing. We have done a few testing on rubber pellet pieces. That was not successful. So what I'm saying is that it depends on the application. So we would like you to contact us and figure out whether it is applicable or not. Another question is that how much drawing efficiency improvement has been achieved over the conventional dryers? The answer is that the best results we have got so far shows 3 to 5 times improvement over the conventional dryers, depending on the configuration. How far it can dry? The answer was in one of my slides. The technology has shown a great potential to dry fabric down to 20% remaining moisture content. Below that level, it is not efficient, but technology is very efficient at much higher moisture content, down to 20%. What will be the final form factor of your dryer? Again, it depends on the final application, whether we are talking about closed dryers, small closed dryers, large closed dryers, or industrial applications. So the design is very flexible, and we can work with you to design the system appropriate for your application. The impact of ultrasonic dryer and the quality of the fabric. So we have not done any study in this field yet, but we are expecting the quality of the fabric and the drawing to be better than the conventional system, mainly because we are not heating the fabric to high temperature. So that reduces the thermal stress on the fabric, and hopefully that's going to help to reduce the stress on the fabric and probably reduce the leak generation during the drawing period. But again, that needs to be tested definitely. How soon will the technology be available in the market? The answer is that it depends on the field of use. For the closed dryer application specifically, they are expecting that the first product to be in the market in somewhere about 3 to 5 years from now. Can the technology be combined with washing machine so we can have a single washer and dryer unit? The answer is that it is possible. Definitely there are going to be a lot of challenges there as well, but that might be one form of the final design, but we haven't actually done that yet. Have you tried drawing multiple layers of the fabric or different type of the fabric? So the answer is that on the small scale system, we draw the multiple layers of the fabric, up to 9 layers as you saw in my presentation, and also we work on four different standard fabric, different type of the fabric, and yes, the technology works for different types of the fabric. What we haven't done so far is to dry much thicker fabric like jeans, and that's one thing that we are going to study in the next phase of the project. Thank you so much for listening to this presentation. If you have any questions, you can always email me. My email address was listed in the first page of the presentation, and we would do our best to answer your questions as best of our knowledge. Thank you so much.
All right. So thanks for joining us today. I'll be telling you a little bit about how to use the root savings calculator. First, a little bit about me. I'm Joshua Newman. I'm a PhD in computer science from the University of Tennessee. I've been full-time staff here at Oak Ridge National Lab for 7 years, and this was actually one of the first projects I became involved with before becoming program manager for software tools and models in the building technology research and integration. That involved projects for websites, web services, databases, supercomputing, artificial intelligence, computer vision, and supercomputing for deep learning. So let me get into the root savings calculator. First, let me start with a little context. Most people are surprised to find out that buildings consume about 41% of the primary energy in the U.S., split roughly between 4.9 million commercial buildings and 114 million residential buildings. In fact, if we look at the energy used for residential and commercial separately, we can see generally heating and cooling our homes is about half the total energy used for our buildings, with the rest made up from water heating, lighting, and then several other use cases of the point. One of the challenges we have in making our U.S. buildings more energy efficient is that the average homeowner only spends about $1,800 a year. So anything that we do to save energy can only save some fraction of that amount, and it usually has to pay itself off in the 6 to 7 years versus we own the home. For it to be cost effective. So that's a big challenge. In the commercial space, we have a little bit more advantage because commercial buildings are typically larger, they need more energy, and so there are things that are more cost effective for commercial buildings. So if you look at all that energy use, there's constantly greenhouse gas emissions. If you don't count nuclear, about 8% of our energy provided in the U.S. is from renewable sources. And in fact, there are future challenges as coal and gas and other petroleum sources are expected to diminish over time, as photovoltaic continues to increase. It becomes an energy security challenge to provide a high quality of life and high energy consumption for all the people around the globe while maintaining the quality of life that we currently enjoy in the United States. In order to address that, we have to look at every possible technology we can as to how to save energy in buildings. Right now, there's something called the root savings calculator that we talk to you about today. What is the root savings calculator? Well, it's a website and a web search. So if you go to rootcalc.com, root as in calculator, rootcalc.com, then you can put in details about your building. You kind of have it. This is my current home. This is what I want to do to my home. Hit calculator will tell you about how much energy and how much money you would save in doing that thing to your home. There's also a web service, so people that are familiar with APIs that don't want to manually click buttons on a website, don't want to process files and software, send it to our simulation server and get the results in your code. There's also a very easy-to-use web service using standard technology. So a little bit about the backstory of how Roof Savings Calculator came to be. It was a large collaboration among several people, the Department of Energy Cooling Technology Program Office, this group from the California Energy Commission, several national labs, Lawrence Berkeley National Lab, Oak Ridge National Lab, some subcontractors, industry partners, all worked together to make the Roof Savings Calculator happen. Well, one of the reasons that the Roof Savings Calculator existed as a project is that there were two main calculators, one from the Environmental Protection Agency, EPA, and the Department of Energy. The problem is that with the same technology, they could be all on an order of magnitude. So you say $50 a year or $500 a year, it was really uncertain. So to create an industry-consistent standard that takes in the estimates provided for energy savings, we really would like the calculator to be the previous calculators as well as the things that the community would like to have as. We also had a challenge in making this usable. So, when you define a simulation of the building, there are literally thousands of parameters that you could use to define the building. Occupancy schedules, how people behave in the building, the material properties of each layer in the wall. But what we wanted to do is make it very simple. So we came up with 20 kind of most important questions that most people know about the building in order to make it easy to put in data into the calculator. We also use very intelligent defaults. We have to survey across the entire U.S. building stock, so we know how Joe, the average American, behaves in a building, and we use that kind of schedule, whether he's in an office or at home. There's different things that he does. So we try to default everything to a national average so that the only thing you have to know to run the calculator is where you're located, what city and state. Most people know that information. So what is the Roof Savings Calculator? Under the hood, it's two simulation engines, one called O21E, which is a whole building simulation package, and then TAKEXM, which does high-fidelity physics simulations of what goes on in a roof and attic assembly. Here you actually see the conduction, convection, and radiation at every surface that TAKEXM is calculated. In fact, TAKEXM is part of a standard called GEDC3490. As part of a standard, it goes through a thorough vetting process review by industry, and before it's accepted as a standard. So what we've done is we tied this high-fidelity physics simulation of the roof and attic to the whole building so that we know if you had insulation or change your roof, how much energy you would save in heating and cooling the home. So it's been used fairly frequently, 54 visitors per day since 2010. It's very popular in hot states that are interested in cool roofing, like California, Texas, and Florida. And if you go to roofcalc.com, you should see a website that looks like this. What does it do? It allows you to put in your building details, your HVAC efficiency and utility pricing, and then you can do a base versus comparison. So if I have this much insulation, I add more insulation to my home, how much energy do I save? You go to this website, you can click on residential or commercial, or whichever building type you're most interested in. The residential building is modeled like this. It's pretty typical home layout. And in the commercial space, we support three building types: the medium office, which is where most people work; we call retail, where most people shop; and then warehouse, where we store our goods that are shipped before they go to the go to where we can buy them. So these are the three commercial building types that are currently supported. And once you go to the website and click on those buildings, this is what you can see. This is basically the input page and the description of the output. So here you have details about the building, your heating and cooling system, then you have your current home, your more energy efficient home, where you add insulation or get a more effective roof. Once you hit calculate, we send all this input data you provide to our calculation simulation engine. It runs for about 2 minutes on average, and then the output data to roll it up into how much dollars a year you would save. That's what most people care about. So let me go into each of these in detail.